Hello everyone, welcome to episode 2 of Hyperbolic Geometry. Today we're going to look at more on hyperbolic line. So let's first recall that our definition of hyperbolic plane. The model we have are following the hyperbolic plane as complex number C on the complex plane such that imaginary part of C is greater than 0. So that's our hyperbolic plane. And hyperbolic line is the line that are parallel to the real axis on the hyperbolic plane. For example, L1 is our hyperbolic line, L2 is our hyperbolic line, and also our semicircle L3 and L4, they are all hyperbolic lines. So we have two types of hyperbolic line. One is Euclidean line, and the second one is Euclidean circle, and the intersection of hyperbolic plane, of course. And what does it mean by parallel? And also, what it means by two hyperbolic lines are parallel. Two parallel hyperbolic lines. Two hyperbolic lines are parallels if they do not intersecting each other. So in our case, L1 is parallel to L2, L3, and L4, but L2 only parallel to L1. To L1, not, hang on, in that case L2 are parallel to L1 and L4, but not L3, etc. Okay, and also we also talk about how to construct those hyperbolic lines on the hyperbolic plane. Construction of hyperbolic line. If given 2 points P and Q are on the hyperbolic plane, P and Q, if the real part of P is equal to the real part of Q, then that would be easy. All we need to do is just construct the Euclidean lines passing through P and Q and take the intersection between the Euclidean line and the hyperbolic plane. And for the next case, if the real part of P is not equal to the real part of Q, to do so, we first construct the line segment LPQ, and then we take the perpendicular bisector, let's call it K, that is perpendicular to the line segment LQ and bisector LP, line LP, so that the intersection point between K and the real axis would be our center. Then we can construct such semicircle. That's the radius, and that's the radius, and then we can construct such Euclidean circle, and the intersection, let's call it D, and D intersection, the hyperbolic plane, is our hyperbolic line. And so the first things different between Euclidean geometry and hyperbolic geometry is the number of parallel lines. For example, in Euclidean geometry, if given Euclidean geometry complex planes, if given a Euclidean line L and a point P, there exists a unique Euclidean line, let's call it L prime, that pass through P and parallel to L. So given Euclidean line L and a point P that is not on L, then there exists a unique Euclidean line L dash such that P is on L dash and L dash is parallel to L. But in hyperbolic geometry, if given a hyperbolic line, if given a hyperbolic line L, let's call it L1, and a particular point P, there exists infinity many lines that parallel to L1. For example, if we construct a other Euclidean line that is parallel to the real axis, pass through P, that is clearly a hyperbolic line perpendicular to L1, let's call it L2. And if we pick an arbitrary point, let's call it X again, actually let's call it Q. Then we have the line segment LPQ, and we construct the perpendicular bisector, and then we can construct the Euclidean circle that pass through P and Q. That is clearly not intercepting L1. So this, I don't know, let's call it A. So A intersection hyperbolic plane is another hyperbolic line that is perpendicular to L1 and pass through P. And since there's infinity many such point Q between L2 and L1, then we can construct infinity many points, construct infinity many hyperbolic lines that parallel to L1 and pass through P. So let's have a look at an example. Given a explicit description of two hyperbolic lines in hyperbolic plane H through I am parallel to the hyperbolic line L such that hyperbolic line is H intercepting set is in complex number plane and the real part set is equal to 3. That's our L. And that's I. So clearly we can construct our first hyperbolic line is just a Euclidean line passed through I and parallel to the real axis. So the first line we have is complex number in the complex plane such that the real doesn't have any real part L1 and intercepting hyperbolic plane, of course. And the second line, we can construct a Euclidean circle that passing through I that pretty much is centers on the origins and have the radius 1, so we can set minus 0 square is equal to 1. Then intercepting the hyperbolic plane. So we have these two hyperbolic lines that parallel to L. And example 2, give a explicit description of two hyperbolic lines in the hyperbolic plane H through eyes again and parallel to the hyperbolic line such that L is equal to H intercepting A, where A is set in the plane such that set past 2 square is equal to 1. So it centers at minus 2 and has radius 1, so that's I. Now, And clearly the first hyperbolic line we can come to our mind, the first one is clearly is L1 equal to the hyperbolic plane intercepting with complex number such that the real part of C is equal to 0. So it's the imaginary line again. And the second one, you want to construct a hyperbolic line that parallel to A intercepting hyperbolic parallel to L and also passing through I. So one way we can do it is using the concentric Euclidean circle. So also that means that it's a Euclidean circle also centered on the same point -2 and has the radius from -2 to I, and that would be, so the radius would be 2 square plus 1 square Pythagorean theorem that is equal to root of 5. So we have a concentric Euclidean circle such that does that. So the second line L2 would be hyperbolic plane intercepting with set in the complex number in the complex plane such that set plus 2 square is equal to root 5 square. It's equal to root 5 square. That is equal to 5. So now we're going to the theorem, or the goal of today is proving the following theorem. So theorem. Let L be a hyperbolic line in the hyperbolic plane H, and let P be a point in hyperbolic plane H not on L. Then they exist infinitely many different hyperbolic lines through P that are parallel to L. So the proof would be really similar to the exercise we have. So proof case 1. Suppose that L is contained in a Euclidean like capital L, since P is not in capital L, then there exists a Euclidean line K through P that is parallel to L. So geometrically speaking would be really similar to what we have in the example, given this is capital L, and this is point P, then we can easily see that there exists a Euclidean line K that passes through point P and parallel to capital L. And since L is perpendicular to the real axis, then we have K is also perpendicular to the real axis. Then we have one hyperbolic line. Hence, we have one hyperbolic line K intercepting hyphen H that passes P and parallel to L. Now we want to construct another hyperbolic lines passing through P and parallel to L. To do so, we pick a X on the real axis such that X lies between K and L. Then we get in here we pick an arbitrary X. Then we can construct a Euclidean circle centered on R and passing through then we can construct a Euclidean circle center on R and passing through P and X. Then we have a Euclidean circle. We have such Euclidean circle A exists since the real part of X is not equal to the real part of P. So the construction is as what we're showing in the last video and also the recall is that we draw a line segment LPX and a perpendicular bisector K. Then we have, and when K intercepting the real line, we call it Y, then we can construct this, the radius Euclidean circle. We can construct that. And since they are infinity many, infinity many points between lines between K and L, then we have infinity many hyperbolic line. parallel to L and passing through P. Now we look at case 2. Case 2. Suppose that L is contained in a Euclidean circle A. So, for example, that's our L, and that is the center. And probably let that be P. And we want to construct a concenter. Construct a concentric construct a Euclidean circle concentric to A and passing through P. And let's suppose the center of A be X, and the concentric Euclidean circle, let's call it D, would be the following. Such that Z minus X square is equal to the distance between X and P, so X minus P squared. And that would be our radius. We can construct such Euclidean circle. And the hyperbolic lines would be hyphen H intercepting D is a hyperbolic line that passes P and parallel to L. Since D intercepting A is empty and is clearly perpendicular to the real axis. Now we want to construct a second hyperbolic line passing through P and parallel to L, and we take any points Y on R such that Y lies between D and A. So let's pick a point Y and let E be the Euclidean circle center on R and passes through Y and P. And to do so, we use the same similar tricks. We first draw a line segment LYP and the perpendicular bisector K that perpendicular to LYP and bisect like LYP, then we can have a circle that's centered at this particular point, and that's not the best drawing, but hopefully you guys get the point. That's not really a good drawing, but yep. Okay, that's not. Yep. Should be something like that, but yeah. Okay. And since there are infinity many points between A and D, then we have infinity many hyperbolic lines. Since we have infinity many points between A and D, then we have infinity many hyperbolic line passes P and parallel to L. Okay, that's all I got for today. Thank you for listening, and I'll see you in the next episode.